Okay, so I just did the experiments where I collided the two carts together, and now what I'm doing is I'm going to show the Logger Pro analysis of the data. So on the left hand side of the screen here, I am showing the force acting on cart 2, that's the green dots, as a function of time. This is recorded using the dual range force sensor that was mounted on cart 2. And also I'm showing the force acting on cart 1 as a function of time. That is measured by the dual range force sensor that's mounted on cart 1. And what Newton's third law of motion claims is that at any moment in time, the force exerted on cart 2 by cart 1 is exactly equal to and opposite to the force exerted on cart 1 by cart 2. And it looks like that doesn't exactly work out in this experiment. So it looks like what we should have is that each of these data points, so if the red is the force acting on cart 1, there should be another point, the exact same value on cart 2. But it looks like they're kind of shifted a little bit compared to each other. So now I'm not quite sure why this is. It's entirely possible that there's a miscalibration in the force sensor. It's also possible, and I think this is likely, that the force sensor, because it can only measure one force at a time, it's basically going back and forth measuring the force on one cart and then the force on the other cart and then the force on the one cart and then the force on the other cart. So it can kind of goes back and forth. So these aren't exactly simultaneous time measurements. Let's look a little bit closer here. So for example, at a particular moment in time, let's say this time right here at 0.7432 seconds, the force acting on cart 1 is negative 11 newtons, the force acting on cart 2 is 19. So either Newton's third law doesn't hold, or there's a problem with the calibration. If we go up right to the peak there, that's the peak. Force on cart 2 is positive 21.5, and the force on cart 1 is negative 15.4. So this didn't work out exactly like I was hoping it would. But in any case, you can see that the forces are definitely in opposite directions, but their magnitudes don't exactly work out like I was hoping they would. You know, what I'm going to do right now is I'm going to just, this is looking ahead to the next part of the lab, but I'll just do some of the analysis right now. What we can do, I'm going to draw right here on the right-hand side, Newton's second law of motion. Newton's second law says that the rate of change of momentum of an object is equal to the force acting on the object, right? So what I'm going to do is I'm going to integrate both sides of this with respect to time. So dp dt integrated over time from time initial to time final should be equal to force integrated over time. This is a definite integral from time initial to time final. And when we do that, you see these dt's cancel out. We're changing variables essentially. dp from momentum initial to momentum final. And this would be the integral of force over time from the initial time to the final time. And when we carry out this definite integration, we'll get the final momentum minus the initial momentum is equal to the integral of our force over time from t initial to t final. So in other words, if we wanted to find out the change in momentum of either of these carts, we could integrate the force over time. So let's go ahead and do that. There's an integration function. So I can integrate the force acting on cart 1. So it's finding the area under this curve between this time and that time. The total integral for cart 1, let me write it over here. So for cart 1, the integral of force over time is equal to negative 0.183 Newton seconds, and that is equal to the change in momentum of cart 1. What about for cart 2? We actually don't need to do this analysis at this point, but let's just do it for fun anyhow. So let's do an integral for cart 2. Okay, that is the area under that curve. So for cart 2, the integral of the force over time is equal to positive 0.184 Newton seconds. Well, that looks pretty good. So that's the change in momentum of cart 2. So looking ahead to Newton's second law, the increase of momentum of cart 2 is really close to the loss in momentum of cart 1. In fact, they're off by only 1 part in about 180. So they're off by, 0.5% or a little bit more than 0.5%. So momentum of the system is conserved to within about 0.5%. That's going to be pretty good. Okay, and maybe I'll say a couple of other things here. The collision, notice the time interval of the collision is very quick, so between about 0.738 seconds. Let's go back here. So the collision really starts at a time of 0.7376, about 0.738 seconds, and really is over by about 0.76 seconds. So it's about 30 milliseconds. So the whole collision, so the collision that we're looking at, the collision lasts about 0.03 seconds, or about 30 milliseconds. Okay, now of course the main thing we were doing in this part of the lab is just trying to see if Newton's third law held, that is, for every force there's an equal and opposite force, and I think the data is less than convincing here.